During the War of 1812, Francis Scott Key unknowingly offered a glimpse into warfare of the next century with his line and the rockets and the bombs bursting in air. But when equipped with a computer to calculate its course, with radio to receive instructions during flight, and radar to detect its target, it then becomes a guided missile delivered with such certainty, one of today's smart munitions has the same impact as a flight of World War II B-17s. The Gulf War, 1991. One by one, smart bombs come of age in the sands of the Mideast.
4, 3, 2, 1, impact. Boom! There's a hit. And, oh yeah. Secondaries, big time secondaries.
I thought that when you could put a hole through the side of a building of your choice and put the second missile through the hole, then you had really done something. We've never seen anything like it in the history of aircraft. You know, there was such a comparison between what we saw in the Gulf War and anything that happened in World War II.
In those few short weeks, the world watched in awe as the latest generation of smart bombs, rockets, and guided missiles took center stage, finding their way to Iraqi targets with relative ease. With one missile for each target, they dissected the numerically superior enemy with surgical precision. The laser-seeking Hellfire, the heat-seeking Maverick, the wire-directed TOW missile, and a host of guided munitions combined to reduce whole army divisions to piles of rubble. But the most devastating missiles launched against Iraqi positions weren't guided at all. Instead, they were fired in mass from the most lethal weapon of its kind, the Multiple Launch Rocket System, the MLRS. Always on the move to avoid enemy detection, the three-man MLRS crews carved their way across the Saudi Arabian desert with calculating efficiency, depending solely on their onboard computer to navigate them. Upon command from their digital radio link, they would pause briefly, arm, and fire.
The American MLRS, the Multiple Launch Rocket System, is a highly effective and highly mobile area rocket system. It's a complement to artillery, but it is a counter-battery weapon, or an interdiction weapon. It can fire rockets over 30 kilometers and cover large areas. You can knock out an enemy battery. You can knock out a supply area. You can knock out tanks when they're still in the formation stage before they make an attack.
In less than 1 minute, it was over. The American commanders called the MLRS the most devastating artillery weapon of the war. 20 miles away, the Iraqis simply called it Steel Rain. First delivered to the U.S. Army in 1972, the MLRS was designed to counter enemy artillery, light armor, and troop concentrations. Each of its 12 rockets contained 644 submunitions, with each bomblet holding the destructive force of a hand grenade. Its onboard navigation system relies on global positioning satellites to orient the launcher to its target. Within seconds, 12 MLRS rockets can cover 30 to 60 acres with nearly 8,000 bomblets.
Being self-propelled and being extremely powerful, you have a very effective and highly mobile striking force and counter-battery force. And it's turned out to be one of the war winners of Desert Storm, and it's going to make quite an effect in any future conflict.
Today, the MLRS is but one of many rocket systems that trace their origins to fireworks back in the 10th century, when man discovered that small measures of sulfur, saltpeter, and charcoal produced brilliant explosions when set afire.
It was the Chinese invention of black powder that allowed them to enter this world and leave hand-to-hand combat and bows and arrows and spears to go into what's kind of the beginnings of the modern-day rocket. Over time, it spread to the European nations. The Europeans first encountered rockets when the British were fighting the Indian armies and were soundly defeated by an Indian contingent of about 5,000 men armed with these rockets that they had learned to design from the Chinese. A rocket had greatly extended the range over which someone could fight their conflict. A kilometer to 2 kilometers, much longer distances than the old bow and arrow and spear could fly.
They were light, they were handy, they were easy to take places where you couldn't use ordinary conventional artillery, but they weren't very effective. They were very inaccurate, and their on-target effects were sometimes doubtful. What they were mainly used for was to frighten the horses or to have a morale effect.
With the advent of the more accurate and powerful rifled barrel artillery piece, rockets fell out of favor with professional soldiers. By the First World War, neither side brought rockets to the front. Instead, they were counting on artillery guns of all sizes to deliver their explosive bombs. The only use rockets had was for signaling flares. But the artillery piece only served to slow troop movements. Round-the-clock shelling from all directions often pinned down the infantrymen, forcing them into an uneasy stalemate of trench warfare. For both sides, the future of bomb delivery rested with the highly maneuverable aeroplane. With thousands of soldiers marching toward the front on any given day, the temptation to bomb them from the air seemed too great for reconnaissance pilots to resist. Beginning with steel darts and hand grenades, these airmen began raining terror on the ground below. Their efforts were quickly sanctioned. In late October of 1915, the British Royal Flying Corps issued a memorandum for all reconnaissance airplanes to be outfitted with the new gunpowder-packed aerial bombs.
They were very often designed more with a spirit of hope than actual achievement, because most of the early bombs were quite simply canisters of explosive, literally dropped by hand over the side of an aircraft. The effectiveness and accuracy was somewhat less than the designers intended, to put it mildly. But towards the end of the war, they were being used to attack marshalling yards, supply areas, towns, generally creating the effects that became so common during the Second World War.
By 1917, military commanders were already looking to the future of bomb delivery systems. With the help of Orville Wright, the U.S. Army attempted to build a flying bomb with a gyro guidance system. The machine, nicknamed the Bug, was a small, pilotless airplane powered by a conventional engine. But the Bug never saw combat. Missile development had to wait until the right kind of guidance system was discovered. 2 years later, an obscure American professor, Dr. Robert Goddard, borrowed the theories of the Russian scientist Konstantin Tsiolkovsky and built an engine that mixed liquid oxygen and gasoline in a combustion chamber. He found that when his liquids were pumped and burned at high speeds, their exhaust produced an extraordinary amount of thrust.
He operated in the Americas, mainly as an adjunct as university research projects, things like that. But his funding was always less than the subject really required. He was operating by himself virtually, or with very small teams. But some of the rockets he produced were very advanced, and some of the propulsion methods, the principles, are still in use to this day.
By the late 20s, Dr. Goddard's rockets were reaching heights of several hundred feet, but in his own country, his work was largely ignored. It was halfway around the world in Germany, where Goddard's research found a receptive audience. In 1927, the Society for Space Travel was founded, and its young scientists eagerly began testing rocket designs of their own. 3 years later, as the group was facing bankruptcy, they received an unofficial contribution of 5,000 marks from officials in the German army, who recognized that rocket research wasn't mentioned in the 1921 Treaty of Versailles. It wasn't long before the Society found another well-heeled sponsor who shared their dreams of conquest in the sky. By 1933, the Nazi Party had come to power in Germany. That same year, the obscure Society for Space Travel was dissolved, and all rocket research came under the control of the German army. The next year, 2 rockets were launched to a height of 1.5 miles. The army was sufficiently impressed. In 1936, they broke ground for a secret research center at Peenemünde on the Baltic Sea and began working on the largest rocket ever, the 5-story high A4. The rocket's design was based on the shape of the German Army's standard 7.92 millimeter rifle bullet. For propulsion, the Peenemünde scientists began testing a combination of 150 proof alcohol and liquid oxygen. Initially, they met with small success. In the years that followed, trainloads of potatoes were diverted from the markets and shipped on site to be mashed and distilled for alcohol, as research on the A4 continued. Still, the German command of the air was unquestioned and unmatched with its wide array of explosive bombs.
Between the wars, bombs in outline and general design changed but little, but their explosives certainly did. Improvements in chemical industry, industrial processes, both towards the end of the Great War and between the wars, meant that pound for pound, or size for size, explosives became much more powerful. They produced a much bigger bang. And some of these more advanced explosives were already in use in aircraft bombs by the time the Second World War started.
On September 1st, 1939, Germany attacked Poland from the air with more than 2,000 planes, disrupting supply lines and military communications while smashing a path for the mechanized army to follow. For the first time, airplanes were used on a wide scale for pinpoint target bombing. The Luftwaffe had no 4-engine high-altitude bombers. Instead, they relied on Dornier DO-17s and Ju-87 Stuka dive bombers to put their bombs on target. The Stukas carried a 500-pound primary bomb and 4 110-pound secondary explosives. Their classic attack position was a steep dive directed at the target. At the last possible moment, the pilot released his gravity bombs and quickly pulled up. The Allies took a different approach to bombing tactics. Their B-25s and B-26s flew low-altitude interdiction missions at high speeds, straight and level. Both the British and the Americans developed long-range 4-engine bombers capable of high-altitude penetration into Germany. At heights above 20,000 feet, the English relied on radar to guide their bombers at night. The Americans flew their bombing missions by day and counted on the top-secret Norden bomb site to strike their targets.
What you would preset into the Norden bomb site was a trail, the distance the bomb would trail due to air resistance behind the aircraft as it descended, and time of fall.
The bombardier had to visually acquire the target to determine an aiming point. For the Norden bomb site to work properly, the bomber had to be flown perfectly level, regardless of distractions.
You had to have at least 30 seconds of absolute straight and level flight. Minimum 30 seconds. Would be great to have 70 seconds because you could synchronize better. When the bombardier had identified the target area, he had the capacity to swing the sight onto the target, and then he could clutch into the autopilot. When he clutched into the autopilot, the bomb sight controlled the airplane.
Once the preset crosshairs reached the target aiming point, the Norden sight automatically released the bombs. The sight put the bomber over target but couldn't guarantee precision. With 10 500-pound bombs apiece, it took an average of 300 B-17 bombers to strike one target in a single mission. The buildings in Germany were often constructed from stone and masonry, requiring bombs with high explosive strength. But in Japan, the architecture consisted mostly of wood and paper, an ideal combination for bombs designed to start fires. On the Marianas Islands in March of 1945, 300 American B-29 bombers were loaded with a new type of bomb, napalm incendiaries. Their destination, downtown Tokyo. The best radar operators were chosen to fly ahead as pathfinders to find and mark the target.
Pathfinders took off about 55 minutes ahead of the rest of us and drew a great cross of fire, like an X, on the ground by dropping their bombs along two intersecting lines. When we came along, our job was to enlarge that cross into a huge fire.
The B-29 bomb bays carried 14,000 pounds of the incendiary bombs, each made from jellied gasoline and magnesium.
This was dropped from the bomb bay in such a way that at about 1,000 feet or so, it was set so that bands holding the bomb together would release, and then it would turn into what we called 38 bomblets, or little bombs, that were filled with napalm, and whatever they hit, they ignited. They stuck to, and they burned and burned and burned.
They scatter everywhere, on roofs, in gardens, in houses, all over the place, and they continue to burn, and heat can build up to such an extent that we get the phenomenon known as the firestorm. Air is sucked in to this maelstrom, and it stokes the fires, so the fires get even hotter. We had this effect at Dresden, in Hamburg. Things like bottles melted, slates cracked, bricks just shattered, and the actual intense heat is absolutely extraordinary.
Now, with this updraft, suddenly the airspeed started to increase. There's only one thing I could do. I started to pull the power back so that I could maintain my altitude. But I quickly found that even though with all four throttles back at idle, this aircraft is going up 2,000 feet a minute, and the speed is increasing. And so I had to allow the airplane to keep climbing to keep from ripping the wings off the airplane.
For strategic bombing theorists of the day, military dominance demanded massive demolition. Consequently, an average of 388,000 civilians lost their lives each month during World War II. The re-emergence of rockets, long ignored in peacetime, was spurred on by wartime developments in solid fuel propellants, and by 1943, thousands of rounds were being manufactured on both sides.
During the Second World War, the rockets really came to prominence as a supplement to artillery. They did not replace artillery. They were a cheap, relatively easy to use alternative that could cover vast areas in a very short time. This ability had to be paid for by the fact that they were relatively inaccurate. In other words, you couldn't be sure that one rocket would hit one target. You had to use them in vast numbers.
Most of the rocket batteries relied on a series of small electrical impulses to set off each round in sequence.
The Germans were among the first in the field with their Nebelwerfer. These were like little six-barreled rocket launchers, later developed into numerous models, but they were used in battalion-sized strengths, as many as 18, 20, 24 of these things going off at once, each firing 6 rockets. And what if you were underneath that lot? It certainly ruined your day.
One of the first successful American rockets was also one of the smallest. The shoulder-launched bazooka fired an armor-piercing shell that could knock out a tank at over 200 yards and was effective on lighter stationary targets up to 750 yards. Another use for the rocket was as a battlefield minesweeper. A variety of naval rockets cleared beachheads prior to amphibious assault operations in the Pacific. Still other models found their way under the wings of airplanes.
When the aircraft pilot aligned the aircraft, got the rocket pods pointed in the right angle, and the rocket left, because the rocket cannot correct its course, the ground target was probably the most vulnerable and the best application of the rocket. They were best used against things that were fairly soft targets. Rockets did not carry highly penetrating warheads, but they may have been carried the type of warhead that would do good against troops or trains or ships, things like that aren't heavily armored.
But perhaps the greatest rocket of all was finally coming of age in Germany. After years of testing, the first successful A4 was launched in October 1942. After the Allies invaded the beaches of Normandy, Hitler turned to the A4 to strike back. He renamed his pet rocket Vergelten II, Revenge Number 2. The A4 was now the V2. In September 1944, the first rockets left their launchers, depended on spinning gyroscopes to find the cities of Paris and London.
There was no need for any control from the launcher. Once the missile left and the right coordinates were put into the computational device, the missile would measure its own speed, measure its own attitude, meaning its angle, and control that attitude and tip its course that when the right range had been accomplished, the missile would tip down and close back on the ground where it was intended to intercept.
The V-2's thrusters burned for 70 seconds, and then they extinguished 60 miles high in outer space. When they returned to the Earth's atmosphere, they picked up speed and screamed down at 2,000 miles an hour.
They couldn't pick the building, they couldn't pick the block where they'd land, but they could probably pick the city where they would hit.
There was no way of retaliating it. There was no defense against it. The only way of defending anywhere against the V2 was to hit it when it was still on the ground before it was launched, which was very, very difficult to do. It made war possible from continent to continent, across oceans. Warfare, until the V2 came along, was restricted to one particular landmass or another. Now it became possible for warfare to be conducted from one landmass to another, from the United States to Europe and vice versa.
By the end of the war, the V-2 attacks killed over 2,500 civilians and wounded thousands more. The U.S. Army made use of guided bombs, but most were unpowered, radio-controlled, free-fall weapons. The Weary Willie was really a B-17 loaded with TNT and outfitted with a remote-control steering system. It was far from a guided missile. On July 16, 1945, another experimental weapon was tested that didn't need guidance at all. At 5 o'clock in the morning, the skies of Alamogordo, New Mexico, shuddered with the thunderous power of 20,000 tons of TNT. The second atomic bomb, nicknamed Little Boy, crossed over the coast of Japan 21 days later. Its target, the nation's seventh largest city, Hiroshima. Population, 245,000. Slowed by a parachute, Little Boy exploded in midair, releasing an unimaginable blast of power that leveled half the city at once. Every structure within 2 miles of the epicenter had nearly vanished. Of the city's 45 hospitals, only 3 were left standing. Besides the atomic blast, the bomb instantly vaporized every structure within 1.5 miles, creating secondary fires that drew winds up to 45 miles per hour, fueling another deadly firestorm.
The original purpose of the atomic bomb was as a super high explosive bomb. They wanted the blast effects. It was the blast effects that devastated Nagasaki and Hiroshima. What they didn't realise was that they were unleashing the power of the atom.
Deadly to human organs, nuclear radiation slowly killed thousands of victims.
The radioactive fallout that would cover a vast area, far bigger than the heat and the blast areas, that would go tailing off for many hundreds of miles downwind, carrying nuclear radiation hazards in its path.
With one bomb, 80,000 Japanese were killed at Hiroshima.
The atomic bomb brought the Second World War to a rapid close. The Soviets exploded their first atomic bomb in September of 1949, but by that time, American scientists were developing something far more powerful, the thermonuclear bomb.
A year later at Bikini Island, atomic bombs were again exploded in the Pacific.
The Bikini tests of 1945-46 was a whole series of them. What they were basically trying to do is to find out exactly what sort of genie they'd actually unleashed from the bottle. It was all very well in theory being able sort of creating the atomic device that went off at Alamogordo in July 1945, and the ones that went off in Nagasaki and Hiroshima. What they really wanted to know was what sort of empirical data could they gain from this device. Actually, how powerful was it? What effects would it have? How far would the fallout go? What effects would it have on targets on the ground? At Bikini, they used warships. But they also had measurement devices on the atolls to measure the blast, to measure the damage inflicted, to work out what sort of casualties they would actually produce.
The atomic testing continued at Alamogordo as scientists wrestled with the power they had created.
It's quite an involved way they measure the effectiveness. It's a rather crude rule of thumb. They measure in what effect would 1,000 tons of TNT going off be. The Hiroshima and Nagasaki bombs were 10 or 20 kiloton bombs, 10 or 20,000 tons of TNT. By the time they finished with atomic bombs, they were up to 500,000 tons of TNT. And some of the hydrogen bomb goes up to 50 million tons of TNT.
By 1952, the Americans were closing in on the hydrogen bomb. In November, they unleashed it with a force 1,000 times the blast of Little Boy. At the close of the Second World War, many German scientists relocated to the United States, continuing their research on liquid-fueled rockets and missile guidance systems. Pellet-based solid fuel mixtures propelled a second generation of tactical rockets that were incorporated in the design of several jet fighters, including the F-86D. The fighters became flying platforms for a variety of 2 3/4-inch unguided rockets. The F-89 Scorpion fighter carried 104 such rockets in the tip of each wing. It was also one of the first interceptors to carry the Genie, an unguided rocket that flew a straight-line course at its target. What the Genie lacked in guidance accuracy, it more than made up for with its atomic bomb warhead. In 1949, the U.S. test-fired its first guided air-to-air rocket, the Falcon.
Those missiles carried either an infrared or a small radar set that would sense radar emissions coming from the target. Those radar emissions were generated by the launch aircraft. A radar beam was pointed at the target. The energy reflected off the target, came back into the front end of the missile, was sensed, and used to guide the missile toward the target. With that advent, with homing missiles, now the target was much more precisely known, and weapon delivery became much more precise.
With a hard-to-find enemy in the jungle below, the use of wide-ranging saturation bombs became routine in Vietnam. Napalm tanks carried 150 gallons of jellied gasoline, which spread upon impact, burning everything in their path. Cluster bombs were introduced as an anti-personnel weapon. The thin-walled canisters burst to spread out hundreds of grenade-like bomblets. spring-loaded air brakes called snake eyes were added to gravity bombs to give low-flying jets a chance to escape their own fragmentations. About the size of 2 refrigerators, Big Blue 82 was one of the largest conventional bombs in the world. Weighing in at 15,000 pounds, Big Blue was so heavy it had to be delivered from a C-130 cargo plane. In Vietnam, it was used to create helicopter landing zones in dense jungle areas with a shock wave that nearly equaled a small nuclear bomb. In Desert Storm, Big Blue was dropped to clear Iraqi minefields in southern Kuwait. By today's standards, the bombing campaign in Vietnam was ineffective. Strategic aircraft were only able to get their bombs within 500 feet of their intended target 50% of the time.
The issue was that we could deliver many, many tons but not strike the specific small target that in fact might be of military interest. The goal became then to be able to steer a bomb very precisely to that target. The experiment we ran at that time was then to point a laser at the target very precisely, to put a kit, in this case a very inexpensive kit, onto the front of that bomb and in fact be able to guide that bomb to where the laser spot was shining. This bomb then consists of a kit that can in fact be attached to the front of the existing bombs that were already in the inventory, already in the warehouses. It has an attachment ring that allows it to just clamp onto those existing systems. On the front was a lens that focused the reflected laser energy from the ground. It would then focus that energy onto 4 detectors mounted on a board, and in fact, if the laser light came in from this direction, meaning the target was off to the left of the bomb would steer that direction. If it were high, it would steer high. So all that was required, in fact, was 4 simple detectors and a simple printed circuit card that would sense where the most energy was falling.
These smart bombs first appeared in the latter stages of the war, often hitting their targets on the first pass and reducing the amount of collateral damage. The 2 3/4-inch rockets, so prevalent on the 50s era jet fighters, found a new and permanent home alongside the UH-1 Huey and Cobra helicopters. Taking their cue from the French Army, U.S. choppers adopted the M3 pods, each capable of launching 24 free-flight rockets at a time. In 1970, the Army replaced its 106mm recoilless rifle with the revolutionary TOW missile.
TOW stands for Tube-Launched, Optically Aimed, Wire-Guided, TOW. And the idea is that it is fired from a tube. The gunner looks through an optical sight aimed at the target, and the guidance system works out how the missile should be guided towards its target and transmits the guidance commands through thin wires to the missile itself. If it hits the target, it will wipe out any modern battle tank.
When mounted on helicopters, with their wires unrolling like a fishing spool, the TOWs were deadly accurate.
The idea was to get instructions from the operator to the missile to tell it which way to turn to stay on course. The operator is observing the missile and observing the target. With a wire, you had a covert, closed communication line that couldn't be jammed, couldn't be heard by an enemy. He never knew that that missile was being fired against him. There was no radio broadcast that he could pick up with a little sensitive receiver and say, aha, I'm being attacked. He didn't know he was being attacked.
The TOWs were so successful in Vietnam that 4 generations of the missile have followed. Today, TOWs can be found mounted on the highly mobile Humvee. The Army's M2 and M3 Bradley fighting vehicles have the TOW built right into them. With their shaped charge warhead, they provide the ultimate ace in the hole against more heavily armored tanks. date, more tows have been produced than any other guided missile.
Tiger Lead, Tiger 2 here. I got a couple of bogeys out there. One coming around at 2 level. Roger, boy, I got it. All right, there he goes. He's going down. You got him. All right, boy, that's a good deal. Roger, we got 4 of them coming in here on at 7 o'clock. Hang on.
First tested in 1953, the Sidewinder revolutionized air-to-air combat. With an infrared seeker inside its nose, the Sidewinder homes in on the heat produced by its target's jet engine. Also introduced in 1953, the larger air-to-air Sparrow missile picks up radar signals from its own jet aircraft once it locks onto an enemy plane. The Sparrow literally rides the beam of radar until it reaches its target.
The infrared guidance that was used in the Sidewinder was effective over fairly short ranges. The missile sensor, the infrared sensor, could only find the heat from the target over a fairly limited range, 5, 6, 7 kilometers of range. Whereas the radar was good at much longer ranges, maybe out to 20 kilometers. So they began to fall into kind of regions of application. Sidewinder in the short range engagements and the Sparrow at the longer ranges.
Although the Sidewinder and Sparrow are perhaps the most successful and prevalent air-to-air missiles today, they must be locked onto their targets prior to launch. The Navy's primary long-range missile, the Phoenix, is one of the most advanced weapons of its kind, using a guidance system that provides high-tech defense for surface ships at sea.
That's a type of guidance where there is a mid-course guidance where the seeker is not yet locked on. A type of guidance where the missile is able to fly in the general direction of the target and then transfer to a terminal mode in which it then is able to see the target with its own onboard sensor.
With microchip technology, the Phoenix is able to turn on its own radar system once it gets close enough to the target.
Now, once they're locked on in their terminal mode, there's no need for any help from the launch platform anymore. But the missile is then able to affect its terminal guidance and kill the target. So the advantage in going to this next generation beyond the Sparrow Sidewinder is extended range of engagement, much longer ranges.
The massive Soviet tank buildup in the early 70s led to the advent of air-to-ground missiles like the Maverick.
The Maverick uses a TV or infrared-like sensor to acquire the target up in the nose of the missile. The pilot flies over the target area, using his onboard sensors, finds the target. Without having to point the aircraft, points the missile seeker at the target. When the missile seeker is locked on, is then able to fire those missiles, affect his launch, turn and go home.
The Apache helicopter was one of the most effective platforms for the Hellfire missile in Desert Storm. Operational since 1984, the Hellfire senses and locks onto its target by finding a laser beam transmitted by another helicopter or soldier on the ground. The invisible laser energy reflects off the target and is picked up in the nose of the Hellfire.
It uses a very sensitive laser reception device, a small camera that senses this radar energy, a camera that's mounted on gimbals or hinges that allows it to point and find that radar energy. Once it finds that radar energy and the missile sensor is locked on, the missile can then be launched, the motor ignited, leave the rail, fly any course it needs to get a good approach on that target, and then fly a collision course and impact the target. And as long as the laser beam is held on the target, that Hellfire missile will hit that target and destroy it.
During Desert Storm, a battalion of Apaches armed with Hellfires destroyed over 100 tanks and 40 armored personnel carriers in the course of just 1 hour. A direct descendant of the Vietnam-era smart bomb is the GBU-15 attachment kit designed to hook onto a 2,000-pound explosive bomb. In the nose of the GBU-15, a TV camera records its flight path after launch. By sending correcting signals back to the bomb fins, the pilot literally flies the bomb into its target. Today, guided missiles have transformed the battlefield to an extent that warfare has reached an entirely new technological plateau. Now that bombs can strike their targets precisely rather than approximately, military commanders have had to reassess the ways conventional wars are fought, thinking of force in terms of precision rather than mass. Compared to 500 feet in Vietnam, today's bombs and missiles are expected to impact their target within 20 feet or less. At the speed in which the computer microchip is developing, missile guidance systems are sure to follow suit.
There are missiles now being developed whereby they're fired off to a general area and they are left hovering in the air either on parachutes or on some sort of very simple sustenance motor until a target appears. It might be a radar, it might be a tank, it might be a ship. Then they will work out, is this one worth going for? Which way is it going? And work out the right path to attack it most effectively, either top attack or from the side, and it will all be done without any operator intervening whatsoever. The missile will do its own work. And that's what the future has to offer.
If future warriors cannot avoid another conflict, at least the lives of innocent civilians may be spared as a result of precise military targeting.
The problems that we have in current warfare are that we have to make that decision as to whether that's truly an enemy target prior to launch. And when you're doing a high-speed engagement against an enemy, you'd like to be able to fire the missile when the conditions are right and let the missile make sure that it's going after the right target, especially if there's a complex scene out there of good guys and bad guys. Kill the bad guy, don't kill the good guy. And that's the way I think the brilliant weapons of tomorrow will be. Bigger computers, more accurate sensors, making the decision in flight as to who's good and who's bad, and doing a good job of it.
With closing speeds between opposing jet fighters often reaching 4 times the speed of sound, a pilot has only a split second to engage his enemy. When the only chance of destroying an incoming ballistic missile rests with defensive ballistic missiles, the value of the microchip on today's battlefield is undisputed.